And here is an amplified view of this particular segment. It is a segment of the rope starting from x, ending at x plus dx. So it's very short. It's x plus dx. Okay, I'm going to have to make an assumption here. My assumption is that the movements, this is y plus dy, right, are very, very small. Okay, so in other words, you do have a wave, okay, but we're not dealing with a wave like this. That's too large. We're dealing with a wave like that. Okay, very smooth wave, which means these angles are very small. Okay, what angle? The angle between the string, this segment of the string, and the x-axis. We're talking about a very small angle. Okay, so that's the assumption to make. Now, since the angle is very small, in other words, it is inclined, but it doesn't have to incline a whole lot. It cannot incline a whole lot. The angle is almost equal to 0. It's almost flat. It's almost horizontal. Okay, so what that means is that this length from here to there is not that different from here to there. In other words, we can pretty much say that the length of the segment is dx from here to there, even though it does get a little bit longer. Okay, what is the mass? Because we want to apply Newton's second law too, right? F equals ma, right? So you have sigma f equals mass times acceleration, right? That's Newton's second law, right? We have to find f, we have to find n, we have to find a. Okay, let's look at m first because I think it's the easiest thing to do. All right, the length from here to there is pretty much dx. Let's say this string is such that per unit length, the mass is mu. Okay, so let's introduce a concept mu. It is defined as dm over dx. Mass per unit length. Okay, we give it a name. We call it linear mass density. Okay. Then from here to there, what is the mass? Well, the mass, you can solve for it. So dm equals mu dx, right? Mu dx. Okay, so that's dm. Let's look at the acceleration. What is the acceleration from here to there? Now remember, I said this segment is so short, it doesn't really matter how you, which point you look at it. This point, this point, this point, they all have the same acceleration pretty much. What is this coordinate? Well, that is the y coordinate, right? And how does this thing oscillate? Well, remember, it's a wave on a string. It's a transverse wave. The wave propagates along the string, yet each segment of the string oscillates up and down in a y direction perpendicular to it. So it oscillates in a y direction. So as time progresses, does x change? What's x? X tells you where this segment of the string is, right? It identifies which segment it is. Since we focus our attention on this segment from here to there, between x and x plus dx, x does not change over time. So what does change over time? Well, that'll be y, right? Y is the displacement of this segment from its unstretched equilibrium position. So from here to there, that's y. Y, of course, changes, so that's how this thing also goes up and down, up and down, up and down. Okay, so displacement is y. It can only move in the y direction. The velocity would be dy dt. And of course, when you look at the acceleration, that would be the second derivative, right? Shouldn't it be the second derivative? A, okay? It's only in the y direction, okay? Only in the y direction. What's that equal to? That would be the second derivative of y with respect to time. So I can write something like this. Okay, now technically, I need to change my symbols because remember, y is not just a function of t. It is also a function of x. Because as you move from one location to another, you're changing one segment to the next segment. Of course, they don't have the same y. So y is a two-variable function of x and t. So when you take a derivative here, what you do here, you leave x as is. You don't change x so that you focus on this particular segment with a particular value of x, right? You don't differentiate with respect to x, you only differentiate with respect to t, and that is, as you know, called partial derivative, and the symbol, as you know, is different. Okay, you have to use partial derivative symbols. That is the acceleration. Okay, we have the mass, we have the acceleration. The only thing left is, what is the net force? Okay, we know that the thing does not move in the x direction. It only moves in the y direction. Let's look at the force and make sure, when you get the force, make sure it does not move in the y direction. I'm sorry, it does not move in the x direction, but it does move in the y direction. Okay, there are two types of forces in the world, contact force and non-contact force. As far as non-contact force is concerned, gravity is the only type we have studied. And I have neglected the gravitational effect for the string. I'm assuming that the string is very light and there's a lot of tension on it, so that the weight of the segment from here to there is negligible. And that leaves us only contact force. Now, this string is in contact. This segment of the string is in contact with the west road through 2 points, left end and right end. Okay, so there's a tension here, pulling it this way, F1. There's also a tension pulling that way, call it F2. Okay, they almost make the same angle with the horizontal, but not quite. This angle is theta 1, that angle is theta 2. They're slightly different. Okay, now, what is the x component of F1? Well, that'll be F1 times what? You go from here to there. That's cosine, right? And it's negative because that direction is positive. So the x component of F1 would be negative F1 cosine theta 1, right? Meanwhile, what about the x component of F2? Well, that would be positive F2 cosine theta 2, right? When you add them together, you get the net x component of the net force on the segment. And what do you think that should be equal to? Well, remember, this thing is not moving left and right along the x-axis at all, so the net force must be 0 because there is no acceleration along the x direction. Okay, what did that teach us about F1 and F2? Now remember, I said these angles, theta 1, theta 2, all these angles are very small, right? When these angles are very small, what do you think the cosine value should be? They're very close to what? Very close to 1, right? So for simplicity, let's say this is 1 and this is 1. I cross them out. So we have negative F1 plus F2 equals 0. What does that tell you about F1 and F2? It tells that F1 and F2 are roughly equal to each other. Okay, so basically that tells you that the magnitude of the tension F is pretty much uniform throughout the entire string. Let me just give it a name. Let's simply call it F. Okay, I don't have to use F1 and F2 anymore. So this is what I learned by using the fact that the string does not oscillate along the x direction. It only moves along the y direction. I found to make that happen, I want to make sure that the tension is pretty much uniform in magnitude throughout the string. Okay, what about the y direction though? You know it does move in the y direction, right? This tells us that the net force in the y direction cannot be equal to 0. Okay, so the question is, what is that force equal to in the y direction? That gives you this much acceleration. Okay, in the y direction, this guy has a component upward, which we call positive. And what's that component equal to? That would be F2 times sine theta 2, right? So you got F2 times sine theta 2. Remember, F1 and F2 are roughly equal to the same value F. So let's call it just F sine theta 2. Okay, F1 has a negative, in other words, downward component in the y direction, which is equal to negative F sine theta 1. You add them together, that is your net force in the y direction, okay? Sigma Fy. Alright? Now, we better hope this is not equal to 0 because it has to give you the acceleration right here. We know there's an acceleration. Since this F and that F, they have the same magnitude, that means theta 1 and theta 2 are not quite equal to each other. Okay, we're looking for the difference between sine theta 1 and sine theta 2. And how exactly does one do that? Well, you know, what exactly is the orientation of F2? F2 points along the tangential line, right? Tangential direction of the string at that point. And F1 points at the tangential direction of the string at that location, right? Now, how does one find the tangential direction? Well, we know the slope of this line here is equal to what? It is equal to tangent to theta 2, right? And the slope of F1, which is along the tangential direction, should be tangent to theta 1, right? But we have sine here instead of tangent. How do you convert sine to tangent? They're not equal, right? But when the angles theta 1, theta 2 are very small, they're almost equal to each other, right? So for simplicity, let's replace the sine with tangent, because we know that doesn't make that much of a difference because the angles are very small anyways. So that's f. Okay, I'm going to take that f out this time and replace sine with tangent. So you have tangent theta 2 minus tangent theta 1. Okay. Exactly what is tangent theta 2? Tangent theta 2 is the slope of this tangent of the tangential line at this location. Okay? In other words, I can write this as, okay, as the slope, which is partial y, partial x at what location? At this location, x plus dx. Now, you notice I use partial y, partial x, not dy dx, because again, y is a function of both x and t, and I'm not changing t here because I got to take the slope for this point and that point at the same moment, right? In order to find the net force at that moment. Okay, minus tangent theta 1, that will be partial y, also partial y, partial x, but at a new location, at this location x. See? Okay, so you see, going from this term to that term is the same function, partial y, partial x, except there is a slight difference, and that is the argument is a little different. This is x, this is x plus dx. And since dx is very small, you expect these two terms to be almost equal to each other, but not quite. How far are they from each other? Well, if I divide this by dx, and I multiply by dx. Okay, let's see what we get. What exactly is this thing in a bracket? Okay, up here I have the difference between partial y, partial x at two locations, x and x plus dx. So really, this is the infinitesimal change in the function partial y, partial x, isn't it? Going from x to x plus dx. And you divide this by dx. So what do you think we're getting? Aren't we getting the derivative of this function, partial y, partial x? Right? So it is the derivative of partial y, partial x. In other words, it is the second derivative of y with respect to x. Okay, so finally we find that this really is just f times the second derivative, okay, of y with respect to x. And don't forget there is an extra dx here. So this is the net force in the y direction. This is the mass. And this is the acceleration. Okay, so again, let me highlight these three. You have F equals ma, right? Here is your F in the y direction. Here is a m, and here is a a in the y direction. Okay, let me apply Newton's second law this time. I say F equals ma. Okay, so the net force in the y direction equals mass, which is dm in our case, right, times ay, right, in the y direction. Okay, what is the net force again in the y direction? Okay, let me copy what I got before. That would be F times second derivative of y respect to x and then dx. Okay, that is the net force in y direction for this little segment. Dm is mu dx. Ay is again the second derivative of y respect to t. Alright, we're almost there. We can then cross out dx, both sides. Okay, cross out that dx. And I am going to move that mu down there. Okay, so I have this. F over mu comes this equals this. Okay, what we have here is an equation for y. If you solve this, you can find y as a function of x and t. Alright, This equation is not an algebra equation, is it? Because there are differential symbols and the unknown function y is under differential symbols, so we call it differential equation. Remember that? Okay, not only is it a differential equation, it is a differential equation about a multivariable function, and you have to take derivative with respect to different variables. So we're using partial derivatives. Therefore, this is also called partial differential equation. Okay. In general, partial differential equations can be pretty difficult to solve as far as our math is concerned. We're not dealing with complicated partial differential equations. However, this equation is different because from physics, we know what the solution might look like. Okay, remember, after all, we're not looking at just any equation. We're looking at this equation for this function. This is a function that describes a wave propagating down a string. Okay, don't we have some idea what this function might look like? As a matter of fact, we do. Now, going back to here. Remember that? I have physical intuition, right? Due to my observation, I know that this pattern does not diminish, and therefore y should be a function of f of x minus vt, right? This describes a wave propagating along the positive x direction with a speed v, right? Now, this is just my intuition. Does it really work? Does it actually satisfy Newton's second law? Well, simple. This equation is from Newton's second law, right? If our intuition works, it is actually correct, then our intuition, which is f of x, y of xt equals f of x minus vt, should satisfy this equation. Okay? If this is actually a solution, then it should satisfy this equation. That means this solution is not only intuitively correct, actually is physically valid because it satisfies Newton's second law. So the only question is this valid? Okay, you got to understand that we're doing something remarkable here because this f, again, can be any smooth differentiable function. It is not just sine, cosine. We have never learned something like that before. In other words, how can a specific equation like this have very, very general solutions? This f can be any differentiable smooth function. We've never learned something like that before. But our intuition tells us that this got to be right because, after all, you can have different forms of wave traveling down a string, and they should all satisfy the same wave equation. Okay, so let's see if this is right. Is it true that this f solves this equation? Okay, this actually can be shown directly. It is possible to solve this equation from scratch. Okay, but we're going to do something easier. We are given this solution. We just want to see if it actually is a good solution or not. So all I have to do is differentiate this thing twice with respect to t, twice with respect to x, and see if the two sides match. Okay, let's do that. All right, how do we do that? Well, it's easy to do. All I have to do is use what's called chain rule. Okay, this whole combination, x and t must appear in this combination. They cannot break away from each other. Let's call this combination u. Let's give it a name called u. So really, this is just f of u, right? What's u? U is defined as x minus vt. Okay, we need to do differentiation twice with respect to x and respect to t. Okay, let's take a first derivative. Okay, so what's partial y, partial x? What's the first derivative? Okay, now y itself is just f of u, right? Isn't it? Because it's just f of u. Okay, so this is just partial f of u, partial x. Okay, we're going to apply what's called chain rule, and you know how that works, right? This is partial f, partial u, and then partial u, partial x. That's how we work out the chain rule. Now, this partial f, partial u, we don't really have to use the partial symbol anymore because f is a function of u only. U is the only variable. So what is that? This thing here? That's just the first derivative of f, right? F prime. We call it f prime. And what exactly is partial u, partial x? Now remember, u equals x minus vt. Okay, when you take a derivative of u with respect to x, you treat t as a constant, what do you get? You get 1, isn't it? Okay, so that's the first derivative. This is f prime. Okay, now let's do the second derivative. We do one more derivative with respect to x. Okay, so here goes the second derivative. What do we have to do? is we have to take this guy, which is the first derivative, take one more derivative, right? So this is partial f prime, partial x, right? And again, let's apply the chain rule. This is partial f prime, partial u, partial x. Okay, partial f prime, partial u. This actually is a straight derivative, normal derivative, because again, f prime depends on u only. So you take derivative of the derivative, that's f double prime, second derivative of f with respect to u. What's partial u, partial x? Again, that's 1. Okay, so we found the second derivative of with respect to x. It's just f double prime. Okay, next, let's look at the second derivative with respect to time t. We can do pretty much the same thing. Okay, so let's do that. Again, first derivative partial y, partial x, partial t this time. Okay, now let's do that. This would be partial f, partial u, and partial u, partial t this time, right? Okay, again, partial f, partial u, we call it simply f prime. That's first derivative. Partial u, partial t. Let's do partial u, partial t. Okay, u is x minus vt. When you do partial u, partial t, you are taking x as a constant. All right, so let's treat x as a constant. Negative vt, v is a constant, t is the argument that you want to take derivatives. So what do you get? Negative v. Okay, that's what you do. Now, next, take one more derivative, second derivative. Again, you take the first derivative and you take one more, right? Now, first derivative has a negative v here. I'm going to take that negative v out. Partial f prime, partial t. Take one more derivative. Okay, now so what's that? Negative v. Okay, partial f prime, partial t. Same thing. Okay, that will be partial f prime, partial u, and then partial u, partial t. Right? Same chain rule. Okay, let's see what we get. We're almost there. Copy negative v. Partial f prime, partial u. That is the second derivative, f double prime. Okay, what is partial t again? That is another negative v. Okay, so negative v squared. What do we get at the end? V squared f double prime. All right, now let's see. When I took the derivative of y with respect to x, second derivative, I get f double prime, right? When I took the derivative of the same function y with respect to t, second derivative, what do you get? I still get f double prime. The only difference is that there is a v squared. Okay, now if you plug this in here and plug this in there, we get actually a match between the two sides. Okay, so this side is f over u, and then you have an f double prime. The other side is v squared f double prime. Okay, so let me write that down. F over u, f over mu, f over mu, and then you have f double prime, right? That equals v squared f double prime. So you see, regardless of what kind of function f it is, as long as it is differentiable, in other words, I took two derivatives, okay, so it's differentiable, I can indeed, believe it or not, cross it out. Any differential function would do. This equation actually is solvable with our trial solution of f of x minus vt, provided that v squared be equal to f over mu. In other words, v equals the square root of f over mu. What is v? That is the speed of the wave. Okay, now given that I can rewrite the wave function by getting rid of f and mu, rather I write it in terms of the speed of the wave v, then I can write it this way. Partial derivative with respect to x equals 1 over v squared, partial derivative with respect to t. This is the famous wave equation. That's the speed of the wave. In particular, it is the speed of wave on a string. The reason why I want to replace f and mu in terms of v squared is because this is more general. It is not only valid for the wave on a string, it is valid for many different types of waves with a speed v. Okay, this is the famous wave equation, and our solution, y, x and t, equals f of x minus vt, is the general solution to this equation. And this wave equation is so important because it describes many different types of waves. How do we know that? Because this f is not just limited to one particular mathematical form. It is any smooth differentiable function. As a matter of fact, this v comes with a squared. In other words, you can replace v with negative v and still you won't change the equation. As a matter of fact, you can change that v, change that sign from negative to plus. This is the same as taking v to negative v. Okay, now what does that mean? It means this is the positive x direction, right? The wave does not propagate this way, but rather goes backwards. Okay, that's what negative v means. So when you see x plus vt, what does that mean? It means that you have a wave, okay, but this time the wave propagates backwards with a speed v, opposite to the positive x direction. That's what this positive sign means. Okay, so what we have here is a very general wave equation, which you will see in many different types of situations, not just wave on the string. And you have also a very general solution, which describes a wave that propagates along the string, or actually along any medium. This is a wave that moves. We call it a traveling wave. Here is the solution to this wave equation. You can also find the speed of that traveling wave, and that is v. Okay, again, the minus and plus sign tells us in which direction the wave propagates.